So here we have an example. Let's read it first. We've got two half equations below, and they show the reactions at the positive and negative electrodes of a lithium cell. And what we have is we have the two half equations given there. Lithium plus an electron going to lithium solid, and then lithium reacting with manganese oxide plus an electron going to lithium manganese oxide as a solid, and we're given the electrode potentials of those two half equations. We're also told that a platinum rod is used as the positive electrode, and we're asked to draw the conventional representation of this cell. Okay, so let's go through it step by step. And the first thing that you probably won't know, that you'll need to know, is that we've been given positive and negative electrodes. Okay, and let me tell you that the positive electrode is the one on the right of the cell diagram. Alright, so in our zinc copper case, that would be the copper one. And the negative electrode is on the left hand side. And so this is where reduction happens. And on the left hand side, the negative electrode, this is where oxidation happens. So that's worth remembering. I'll go over it again. The positive electrode is written on the right hand side, and at the positive electrode, that's where we get reduction reaction. And the negative electrode is written on the left hand side, and that's where we get oxidation. And one other side thing to notice is that we're calling them positive electrodes and negative electrodes. And the reason for that is that calling them anodes and cathodes can get confusing, because you're probably used to anodes being positive and cathodes being negatives, but that's only with electrolysis. When you're looking at galvanic cells, which is another word for what we're using here, it's the other way around. So the anode is the negative and the cathode is the positive. So anyway, let's just stick with the rule that we've written in blue on the left hand corner there. That's the first thing to notice. And then the second thing to notice is that we need to decide which of these is going to go on the left and which of these is going on the right. So we're going to use the rule from the earlier slide. The most negative electrode potential goes on the left hand side, and the least negative is going to go on the right hand side. Right, so that's the first little clue that we've got as to how to write this representation of the cell. So the next thing for us to do then is to write down which is our oxidation reaction. Which is our oxidation reaction. So we know that the lithium ion to lithium solid reaction is going to go on the left hand side, and that's the oxidation reaction. So let's write that down as an oxidation reaction. So lithium solid is going to go to a lithium ion giving up its electron. Okay, so we know that because it's the most negative electrode potential, but in the question it's always written as a reduction reaction, but we know that in that cell, that's on the left hand side, it's going to be an oxidation reaction, and so we're going to write, we're just going to reverse that half equation that's in the question to write it as an oxidation reaction. Okay, so in the same way, let's do our reduction reaction. So we know that the reduction reaction is going to happen at the right hand side, so we're going to use the second half equation, and that's already written as a reduction reaction, right? So we can just copy it down. So the lithium ion in aqueous solution plus the manganese oxide, right, plus an electron is giving lithium manganese oxide as a solid. So now we've written our oxidation reduction reactions down. So then the next step is to write out the reactants and products of the oxidation reaction, followed by the reactants and products of the reduction equation. So our reactants, let's go back to blue. Okay, so we've got lithium, so our reactant, and lithium ion, so our product. And for our reduction reaction, our reactants are lithium ion, manganese oxide, and our product of the reduction reaction is lithium manganese oxide. Next step is to put in our salt bridge between the two half cells. So we've written the two half cells in two different colours, so it's clear where the salt bridge should go. And if you remember, we write the salt bridge as double vertical lines. That's that. And so then the next step after that is to add in the phase boundaries. Let's do that in black as well. All right, so the phase boundary is going to be between the reactants and the products of each half cell. So in the lithium, in the oxidation reaction in blue, we have solid lithium and aqueous lithium ions. So they're in different phases, so we're going to write that as a vertical line. And in the reduction reaction, we have lithium ions and we have manganese oxide, lithium ions being aqueous and manganese oxide being solid, so we can, that plus shouldn't be there, let's just overwrite it, that should be a vertical line to give the phase boundary there. But we also, as products, we have two products here, we have the manganese oxide and the lithium manganese oxide, and they are in the same phase, they're both solid, so we're going to have a little comma in there to separate those. So the last thing to put in here is to remember the platinum rod being used as the positive electrode. Now, because it's a positive electrode, is it going to go on the left-hand side or the right-hand side? Well, from the earlier discussion, you can remember that it's going to go on the right-hand side. And so we draw a vertical line to separate it, and we're going to give the chemical symbol of platinum there to signify the platinum rod being used as the positive electrode. And there we have it, QED. So let's do another example. This time, let's do it the other way around. Let's say we're given a conventional representation of a cell, and it is an aluminium and lead cell. And what we were asked to do is we were asked to write half equations for the reactions occurring at the positive and the negative electrodes. So the first thing you'll remember is that at the positive electrode is on the right hand side, and that's where reduction happens. Remember that from the previous slide. And then the corollary is the negative, so that's going to go on the left hand side, and that's where oxidation happens. And now we can write out some half equations. Shall we start with the positive electrode? So the positive electrode, we've got a reduction reaction, and so that's going to be Pb2 plus, gaining 2 electrons, reduction is gain, gaining 2 electrons, and we always write it as an equilibrium reaction to make lead solid. Okay, so that's the reaction happening at the positive electrode, and at the negative electrode we know that that's an oxidation reaction, and so the oxidation reaction is going to be aluminium metal, and that's going to be making aluminium ions, and you remember that they are 3+ ions, and they're giving up, oxidation is loss after all, they're giving up their 3 electrons. And there's the question answered. Easy as that. So as we know already, each half cell or each electrode has an electrode potential, the amount by which it wants to accept or donate electrons. So that means that the whole cell must have a potential, as it does. And that is given the following symbol. E for electrode, and this is the standard sign. Standard, looks like a tube sign, a circle with a horizontal line through it. That is the symbol for the standard electrode potential. And here we're going to give you a formula for calculating the electrode potential of a cell. Okay, so the electrode potential of a cell is the electrode potential under standard conditions of the right hand side, take the electrode potential under standard conditions of the left hand side, where the right hand side is the reduction and the left hand side is the oxidation, as you're familiar with already. So if we use the zinc copper cell as an example again, we can work out the actual voltage of that zinc copper cell under standard conditions. So on the right hand side, if you remember, that was the copper, and if you refer back, then the electrode potential of the copper half cell was positive 0.34 volts. Okay, and then we're going to have minus the electrode potential of the left hand side, that was the zinc side, and so if you remember, the electrode potential of the zinc was minus 0.76. Okay, so that just works out at plus 1.10 volts, and that is the electrode potential of the zinc copper cell. It's a galvanic cell under standard conditions. And what you might be given is you might be given the electrode potential of the cell and one of the half cells, and you'd have to work out the other half cell. So you do have to remember that it's right hand side take left hand side, and then after you've remembered that, it's easy because you've got an equation with 3 variables in it, and you'd be given 2 of them, so you just rearrange to find the third one. And we can try such an example if you like. So here is our example. We've got a cell, and it's been given an EMF of plus 2.00 volts. It's an aluminium copper cell, and the standard electrode potential of the copper half cell is 0.34 volts, and it wants us to calculate the standard electrode potential of the aluminium half cell. Okay, so of course the first thing we're going to do is write down our standard equation. So we've got the electrode potential and standard conditions of the cell. It's going to be equal to the electrode potential of the right hand side minus the electrode potential of the left hand side. Okay, which is which? Well, we can see that copper is going to be on the right hand side and aluminium is going to be on the left hand side. So, and we're given the electrode potential of the cell as 2 volts. So 2.00 is going to be this variable. The right hand side is going to be 0.34, and that leaves us with what we require, the electrode potential of the left hand side, which is the aluminium. So we're just going to rearrange this equation. Why don't we add the left hand side to both sides, and then take 2 from both sides. So we rearrange like that, and that's going to come out to be minus 1.66 volts. Done.